Hi, welcome to the next session of the subject Engineering Maths. We were discussing chapter 7, that is numerical methods, and in this session we discussed numerical integration. In last two sessions we have discussed solving algebraic and transcendental equations by using four iterative methods, right? Newton-Raphson method, bisection method, Regular-Falsy method, secant method. After that we have discussed numerical differentiation, that is multi-step methods. So we have gone through Runge-Kutta methods of order 1, 2, 3, 4, etc. Now in this session, that is subtopic 3 of numerical methods, that is numerical integration. Right? Now, actually my basic task is to find this integral a to b f of x dx. Basically what this represents is, this is nothing but area bounded by the curve f of x between the straight lines x equal to a and x equal to b. So geometrically this represents area bounded by f of x between the lines x equal to a and x equal to b. Between the lines x equal to a and x equal to b. Of course, the function f of x must be continuous in closed interval a comma b. So we know that continuous function means its graph must be continuous. So the graph must be continuous. It can have deviations, but the graph must be continuous between the boundaries x equal to a and x equal to b. Now let me tell you one simple example. That is by finding integral value in the regular pattern. That is, suppose I can do integral 1 to 2 x square dx. So when you do in the normal way, this value becomes x cube by 3. So integral from 1 to 2. Values are ranging from 1 to 2. So apply upper limits followed by lower limits. It gives me 8 by 3 minus 1 by 3. This is 7 by 3. Therefore, the area bounded by x square between the boundaries x equal to 1 and x equal to 2 is 7 by 3 square units. So geometrically, if I draw the graph of this function, this is x square, parabolic shape, and say for example this is the line x equal to 1 and this is the line x equal to 2. So this curve is y equal to x square, and this shaded region is 7 by 3 square units. This is 7 by 3 square units. Of course this is exact value, but when we do not have these techniques, in olden days people used to find numerical integration by using various iterative methods. Just what we have done in case of numerical differentiation, we have followed multi-step methods. The same things more or less we do the same even for numerical integrals also. But whatever the values we get by using numerical approach, those values may not be accurate. They have some deviations from original values, but in the olden days people used to follow these techniques only. After that, when technologies have been improved, then people have gone through direct integral values. Okay, so let us try to get these values. Okay, so at first note these points. Let y equal to f of x. Let y equal to f of x be a function which is continuous in closed interval a comma b. Let y equal to f of x be a function which is continuous in closed interval a comma b. Then integral a to b f of x dx. Then integral a to b f of x dx is nothing but, then integral a to b f of x dx is nothing but area bounded by the curve f of x, area bounded by the curve f of x between the lines x equal to a and x equal to b. Area bounded by the curve f of x between the lines x equal to a and x equal to b. Right? Now our next task is how to evaluate these integrals using numerical approach. This is my curve f of x, which is continuous in closed interval a comma b. Now my task is how to find integral a to b f of x dx. Now let me draw the graph of this function between the lines x equal to a and x equal to b. So this is two-dimensional coordinate system, x-axis, y-axis. Suppose the curve is like this. This is the curve y equal to f of x. And this is the line x equal to a and this is the line x equal to b. So it is represented by this. Now how to get this? This shaded region I need to find out this. So in order to get this shaded region, I will divide this closed interval a comma b into finitely many partitions or rectangles, or we can call them as squares also. But length of each partition must be uniform, right? Suppose see, I will call lower limit as x0, upper limit I call it as xn. So divide this into many number of partitions. So the starting point is x1, next point is x2, x3, so and so on. The last but one point I name it as xn minus 1. Now draw lines parallel to x-axis. Just now we have drawn line parallel to y-axis. Do the same for lines parallel to x-axis. Now I call it as, for example, this is R1, rectangle, partition, or sometimes it may be square. That depends on width as well as breadth. Now this is R2, this is R3, this is R4, this is R5. Therefore, here the length between consecutive points must be uniform, and that we must be call it as subsize. Symbolically we write it as H, right? Now this is R1, R2, R3, R4, R5. So here length must be same for each partition. We can call them as partition or subinterval or rectangle, or sometimes it may be square. So more technically we call them as partitions or subintervals. So this is one partition, second partition, third partition, fourth one, and so on. So length must be uniform and breadth may be frequently changing. That depends upon shape of the curve. So therefore when you try to find this value, this is nothing but area of R1 plus area of R2 plus and so on plus area of R5. This is area of R5. So area of R1 plus area of R2 and so on plus area of R5. So area of each partition will be length into breadth value. Length is this one and breadth is this one. Now what is the difference between consecutive x values? That I call it as H. So H will be called as step size. And this is nothing but basically the difference between consecutive x values. x1 minus x0 equal to H. Similarly, x2 minus x1 equal to H. x3 minus x2 equal to H. When you do like this, finally we get xn minus 1 equal to H. Of course, this x0 is lower limit and this xn is upper limit. Okay. Now what is this n? This n represents the number of subintervals. N represents number of subintervals. So when you combine all these, the relation we have is x1 equal to x0 plus h, x2 equal to x1 plus h. So similarly it will be like this, xn equal to xn minus 1 h, xn minus 1 plus h. Now when you combine all these inequalities, finally the result becomes xn equal to x0 plus nh. Xn equal to x0 plus nh, where this is upper limit and this is lower limit, number of subintervals, and h is called step size, which represents the difference between consecutive x values, right? So this is the way. See, in this case we have divided this shaded region into 5 partitions. So this is not a mandatory. In this case, as an example, I have divided this shaded region into 5 number of rectangles or partitions or subintervals. But depends upon the length of the curve, depends upon the width of the curve. So I can divide this interval into many number of partitions. I mean many means finitely many, always finitely many. So this is the way like this. Now to evaluate this, we have 3 iterative methods in the form of trapezoidal rule, Simpson's 1/3 rule, and Simpson's 3/8 rule. Okay. So note all these points. Now at this point, you specify that x naught is lower limit, x naught is lower limit, xn is upper limit, x naught is lower limit, xn is upper limit, n is the number of subintervals, n is the number of subintervals, and h is the difference between consecutive x values. H is the difference between consecutive x values, which is called as step size. Which is called as step size. Now we discuss three iterative methods to find these numerical integrals, right? The first iterative method we need to discuss is trapezoidal rule. Now let us see. Suppose we have a function y equal to f of x with the following tabular values. X values are x1, x2, x3 and so on, xn minus 1, xn. Y values are y0, y1, y2, y3 and so on, yn minus 1 and yn. Now in this data we have n plus 1 values. We have n plus 12 values. So x1 to xn we have n values, add this value. So totally we have n plus 1 values. What does it mean is we can divide this area into n subintervals. N subintervals of equal length. N subintervals of equal length. Now my task is to find integral x0 to xn f of x dx. The lower limit generally I represent it as a, upper limit I represent it as b. Therefore, the value of integral a to b f of x dx using trapezoidal rule is given by this vt, where vt is value by trapezoidal rule. So symbolically we write integral a to b f of x dx, and this is given by h by 2 into the starting value of y is y0, last value of y is yn. So y0 plus yn plus 2 times sum of remaining y values. So y1 plus y2 plus and so on, last but one y value, that is yn minus 1. Therefore, this is nothing but value of by trapezoidal rule to get integral a to b f of x dx. H by 2 times, h is step size, that is the difference between consecutive x values. H by 2 times sum of first and last y values plus 2 times sum of remaining y values. Now in this case I can discuss its error also. Error by trapezoidal rule. This is error by trapezoidal rule. So this value is nothing but OV minus VT. ET equal to OV minus VT, where OV is nothing but original value. Original value means value by direct integration. Value by direct integration, and this is also called as closed form method. Value by closed form method. So therefore the difference of these two values will give us the error. Original value minus value by trapezoidal rule. So whenever this difference is 0, error is 0. In that case, that particular integral is giving accurate value. That means trapezoidal rule is giving accurate value for that particular integrand function between the limits a and b. Okay. So note down this. Let y equal to f of x be a function. Let y equal to f of x be a function with the following data. Let y equal to f of x be a function with the following data. Write this tabular form. Let y equal to f of x be a function with the following data. have this tabular form. X values are like this, Y values are like this. Then Vt equal to this. After that, you write these points. This is error by trapezoidal rule. Error by trapezoidal rule. That is a T rule. Note down these points. Note, if the data contains n plus 1 values, if the data contains n plus 1 values, then there will be n equal subintervals. Then there will be n equal subintervals or n subintervals of equal length. If the data contains n plus 1 values, then there will be n plus 1 subintervals of equal length. N subintervals of equal length. Pardon. I repeat once again. If the data contains n plus 1 values, there will be n subintervals of equal length. Now, our next task is how many subintervals I need to choose if I want to solve integral a to b f of x dx using trapezoidal rule. That gives me important factor. So that is the crucial thing. So therefore, the number of subintervals required to get integral a to b f of x dx using trapezoidal rule is multiples of 1. That means you can take n value 1, 2, 3, 4, 5, etc. All these are multiples of 1. Always you need to decide, because you may ask me how many subintervals you need to select. That varies from procedure to procedure. That is rule to rule. So for trapezoidal rule, you have a number of subintervals as multiples of 1. For Simpson's 1/3 rule, it is multiples of 2. For Simpson's 3/8 rule, it is multiples of 3. Why it is like this? Let me give explanation by taking different examples so that you can understand very easily. So for the time being, you try to remember that the value of n is multiples of 1 in case of trapezoidal rule. Note this. The number of subintervals required for trapezoidal rule is multiples of 1. The number of subintervals required for trapezoidal rule is multiples of 1. That is n equal to 1 or 2 or 3, etc. n equal to 1 or 2 or 3, etc. Okay. Next we discuss Simpson's 1/3 rule. Suppose we have y equal to f of x with the tabular values like this. Then we can get the value of integral using Simpson's 1/3 rule like this. The value will be like this. I denote it as v1/3. Value by Simpson's 1/3 rule. This is nothing but integral a to b f of x dx. So this is given by x/3 into x plus 4 into o. This is x, this is multiplication. 4 into o plus 2 into e. Now I need to say what is x value, what is o, what is e. So here x is sum of first and last y values. X equal to sum of first and last y values. So this is nothing but y0 plus yn, because this is the starting value of y and this is the last value of y. Now what O represents? O is sum of y values with odd index. Sum of y values with odd index. This is most important thing. Odd index. Generally odd index starts from y1. So 1, 3, 5, etc. This is nothing but y1 plus y3 plus y5 plus and so on. Now what is e? This is nothing but sum of y values with even index. Sum of y values with even index. Generally even index starts from 0 onwards. Even index starts from 0 onwards. But y naught is already covered in x. So that should not be taken. When a quantity is covered in x, that should not be covered in O and E. If a quantity covers in E, that should not be covered in any one of the parts. So at any time, one y value must be contributed to either x or O or E. So sum of y values with even index. So therefore, this is y2 plus y4 plus y6 plus and so on. Now here also we can measure error values. So error values are given by this. Error by 1/3 rule I represent by E1 by 3. This is nothing but OV minus V1 by 3. OV means value by direct integration. Now this is the way to get error value as well as V1 by 3. Now my next task is what could be the number of subintervals in case of Simpson's 1/3 rule. So in case of Simpson's 1/3 rule, the number of subintervals required is n value, that is multiples of 2. So 2, 4, 6, etc. So I give explanation why it is multiples of 2 within few minutes. Okay. So note all these points. Note the number of subintervals required for Simpson's 1/3 rule is multiples of 2. The number of subintervals required for Simpson's 1/3 rule is multiples of 2. That is n equal to 2 or 4 or 6 or 8, etc. So please try to differentiate. This is multiplication, but this is x, right? Next, I will go for Simpson's 3/8 rule. The last iterative method to get value of integral a to b f of x dx. So we have a function y equal to f of x with this tabular form. Then the value of integral using 3/8 rule is represented by v 3/8. This is integral a to b f of x dx. And this will be modified like this. The value will be 3h by 8 into x plus 2 into capital Y3 plus 3 into r. 3h by 8 times x plus 2y3 plus 3r. X is as usual sum of first and last y values. So that is y0 plus yn. Next I need to discuss what is y3. So this is sum of y values with index multiples of 3. So this is sum of y values with index multiples of 3. But generally people will take the tabular values which are multiples of 3. No, you need to maintain index. Sum of y values with index multiples of 3. Therefore, this becomes y3 plus y6 plus y9 plus and so on. Index must be multiples of 3. And what is r? Sum of y values, that is with the remaining index. So simply I can write it as sum of remaining y values. Sum of remaining y values. So this is the way to get integral a to b f of x dx using Simpson's 3/8 rule. 3h by 8 into this. This is sum of first and last y values. Y3 is sum of y values with index multiples of 3. R is sum of remaining y values. At any time, one value of y will be contributed to either x or y3 or r. What is point? See, therefore, when you are solving numerical integrals using these methods, particularly for Simpson's rules, you please maintain the index y0, y1, y2, etc. In case of trapezoidal rule, it is not required because you always consider sum of first and last y values plus 2 times sum of remaining y values. So even though if you do not maintain index, you won't get any problem. But in case of solving problems using Simpson's 1/3 and 3/8 rules, please maintain index properly. Otherwise, there is a chance to get wrong selection of values. Okay. Now, in this case, as usual, we can find error. So this is error by using 3/8 rule. E 3/8 equal to OV minus V 3/8. Now, one of the important factor is about number of subintervals. In case of solving problems using one-third rule, the number of subintervals must be multiples of 3. So n equal to 3 or 6 or 9, etc. Right? So note all these points. Note the number of subintervals required for 3 by 8 rule is multiples of 3. The number of subintervals required for 3 by 8 rule is multiples of 3. So you can easily remember the sequence. For trapezoidal rule, it is multiples of 1. For Simpson's one-third rule, it is multiples of 2. For 3 by 8 rule, it is multiples of 3. Now I give explanation why it is so by taking different examples. Okay. So we discuss examples. First one, let us solve integral 0 to, say for example 10, 2x plus 1 dx using trapezoidal rule with h equal to 2. H value is nothing but step size. So let us evaluate this integral using trapezoidal rule with h equal to 2. After that we try to find error also. So this is my f of x. F of x is 2x plus 1. H value is 2. This is lower limit, this is upper limit. So let us have the tabular representation. X values are 0, 2, 4, 6, 8, 10. F of x values. So replace x by 0, in this case you will get 1. Next x becomes 2. So this becomes 5. Next x becomes 4. So 2 4 is 8 plus 1 9. So they maintain a gap of 4. So this becomes 13. This is 17 and this is 21. This is starting value of y and this is last value of y. Therefore value by trapezoidal rule is h by 2. H value is this. So I will write the formula, or you can do directly h by 2. H value is 2. So 2 by 2 into sum of first and last y values. It is 1 plus 21 plus 2 times sum of remaining y values. 2 times remaining y values are 5, 9, 13, 17. 5 plus 9 plus 13 plus 17. Now this is nothing but 22 plus, this is 2 times of, so this is 13 plus 17, 30, 30 plus 14, 44. So therefore this is 22 plus 88. Therefore this gives me 80 plus 20, 100. This is 110. So value by trapezoidal rule is 110. Let us find original value, that is value by direct integration. So integral 0 to 10, 2x plus 1 dx. So this is x square plus x. Limits are from 0 to 10. So replace x by 10, 10 square plus 10. This is 110 minus 0 plus 10. So this gives me 110. So interestingly, the value of Vt is 110. The value by direct integration gives me 110. Therefore, the value of Et is 0. So therefore, error is 0 means for this function. So generally, when you are integrating a function, this will be called as integrand. This will be called as integrand. So therefore, if the integrand is a polynomial of degree 1, this is a polynomial function of degree 1. So trapezoidal rule gives always 0 error for all first degree polynomials irrespective of number of subintervals. That's why we start always n with multiples of 1. So here integrand is a polynomial function of degree 1. That's why we always choose number of subintervals as multiples of 1. But it always gives 0 error. You start with any integrand as a polynomial of degree 1, do with trapezoidal rule, do by original value, find the difference, error will be 0. Right? Note these points. Even you can try this by taking h equal to 1, the same function by taking h equal to 1. When you take h equal to 2, how many points are there? 1, 2, 3, 4, 5, 6. So 5 subintervals. First subinterval, second, third, fourth, fifth. Suppose when you start the same problem with h equal to 1, number of subintervals will be more. So here it is 5, there it will be 10. Again you will get same error. You can cross check it. Not this point. Trapezoidal rule gives zero error. Trapezoidal rule gives zero error for all polynomials of degree 1. Trapezoidal rule gives zero error for all polynomials of degree 1, irrespective of number of subintervals. Most effective point. Trapezoidal rule gives zero error for all first degree polynomials, irrespective of number of subintervals. Right? This is the reason why we start number of subintervals always as multiples of 1. Now let us solve another problem by using Simpson's one-third rule. So let us start with this. Evaluate integral 1 to 5. I is to maintain h value 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. 4 subintervals will come. 1 to 2, 2 to 3, 3 to 4, 4 to 5. Suppose the function is this. Suppose x square plus 1, or I can say, for example, 3x square plus 1. So that calculation will be simple for me. Even if you take x square, it works. So integral 1 to 5, 3x square plus 1 dx by one-third rule with h equal to 1. With h equal to 1. This is a second degree polynomial expression. So f of x equal to 3x square plus 1. Tabular values. Lower limit is 1. Maintain h value 1. So 1 plus 1. 1, 2, 3, 4, 5. So here f of x values are 3 into 1 square plus 1. So this gives me 4. 2 square, 4. 4 into 3, 12 plus 1, 13. 3 square, 9 3 is 27 plus 1, 28. 4 square, 16. 16 3 is 48 plus 1, 49. 5 square, 25 3 is 75 plus 1, 76. Let us maintain index for this y0, y1, this is y2, and this is y3, this is y4. Therefore, the value of integral using one-third rule is h by 3 into x plus 4 into o plus 2 into e. Here the value of h is 1. So 1 by 3 into x value is sum of first and last y values. 4 plus 76 plus 4 into odd index. These are odd index values y1, y3. So y1 plus y3, 13 plus 49. It gives me 62, or I can do like this, 13 plus 49 plus 2 into even index means already y4 is covered, now only y2 is left. So it is 28. So 1 by 3 into this is actually 80 plus this is 4 into 62. 62 4s, so 8, 248. So this is 248 plus 56. So therefore this is 1 by 3 into this is 240 plus 80, 328 plus 56. So 28 plus 56 is 84. So this gives me 384 divided by 3. Value by one-third rule is 384 by 3. Now let us solve by taking original value. Original value is integral 1 to 5, 3x square plus 1 dx. So this is x cube plus x. Limits are from 1 to 5. 5 cube is 125. So this gives me 5 cube is 125 plus this is 5 minus this gives me, so 1 cube plus 1, this is 2. So this is 123. Sorry, this is 120, 130. 130 minus 2, 128. Of course, this is also, so I think so this is 128. 3 12, 3 120s, 360 plus 3 is 24. So that is 128 and this is 128. Therefore, the value of ET is 0. Therefore, why we are getting 0 error is it is a second degree polynomial expression. Therefore, Simpson's one-third rule gives 0 error for all second degree polynomial expressions irrespective of number of subintervals. That's why we always start with number of subintervals as multiples of 2 when you are dealing with one-third rule. Note these points. One-third rule gives 0 error. One-third rule gives 0 error for all second degree polynomials. One-third rule gives 0 error for all second degree polynomials.